Hello, this is Dr. Hanaa Assil, and this is part 3 of the review on Modular Unit 2 for the IGCSE Chemistry Edexcel. So, let's talk about air and air pollution. So, remember that the percentages of these gases in air, you are required to know that nitrogen is 78%, so this is the most abundant gas. Remember, the word abundant means present in highest amount. So the most abundant gas in air is nitrogen, 78%. Then oxygen, 21%. Remember that argon is the noble gas in the air, and this is 0.9%. Carbon dioxide is 0.03, or sometimes we say 0.04%, and water vapor is variable. Usually we talk about experiments to determine the percentage of oxygen. This could be one of them, in which we have copper wire that we're heating in air, so of course it's going to react with oxygen to form copper oxide. And we are starting with a certain amount of air in the syringes. We're going to push this air over the copper until there is no more change in volume. Of course, as the copper takes oxygen from the air, the volume in the syringes becomes smaller. Now, relating this final volume to initial volume, you can determine the percent oxygen in the air. Of course, you should remember that when we start with copper, copper is a reddish-brown solid or a reddish-brown metal. Now, when it reacts to form copper oxide, it becomes black. Formation of carbon dioxide. What forms carbon dioxide? Of course, we learned about complete combustion of fuel or complete combustion of hydrocarbons. This gives carbon dioxide plus water. We can also form carbon dioxide by thermal decomposition of carbonates. So if I heat copper carbonate, which is a green solid, it will form copper oxide plus carbon dioxide, and the copper oxide, of course, is a black solid. Remember, the problem with carbon dioxide is that it is a greenhouse gas. That means it traps the heat of the sun in the atmosphere. You know that naturally the heat coming from the sun, most of it should reflect back into space. But when we have a lot of carbon dioxide and there are other gases such as methane, when they increase in the atmosphere, these trap the heat of the sun, prevent its reflection out of the atmosphere, and this causes what we call global warming, leading to climate change. Okay, let's talk about chemical tests. You are required to know tests for anions, cations, and gases. So, carbonate, how do we test for carbonate? If we think that the solid is a carbonate, what we do is add acid. So, specify an acid. So, usually we say add dilute hydrochloric acid. Of course, acid with carbonate should give carbon dioxide gas. So, our observation is bubbles of gas that turn lime water milky. If we're asked to name the gas, then we say carbon dioxide. Remember that what we have in there is lime water, and lime water becomes milky when CO2 is bubbled through it. Test for halides, chloride, bromide, iodide. All of them have the same test. We add dilute nitric acid and aqueous silver nitrate. If it's a chloride, it gives a white precipitate. Bromide is cream precipitate. Iodide is yellow precipitate. You are required to know all of these tests. Now, what is the test for sulfate? Remember, sulfate, we add dilute nitric acid, then add barium nitrate, or we could add hydrochloric acid and barium chloride. So nitric acid, why do we add acid first? Remember, we're adding acid to remove any carbonate that may be present, because if I don't have sulfate but I have carbonate, I will still get a white precipitate. So we add the acid to remove any carbonate that would be present, and then when we add the barium nitrate and it gives a white precipitate, then I know that it is sulfate. Test for ammonium, and I'm going to remind you there is test for ammonium, and ammonium means aqueous ammonia or a solution of ammonia. So test for ammonium, I add aqueous sodium hydroxide. Remember, ammonium ions, I react it with a base like sodium hydroxide. On warming, bubbles of ammonia gas are given off that turn damp red litmus paper to blue. Remember, when we test a gas, the litmus paper has to be damp because litmus paper works with water. So either you're going to put it into a solution, or to use it to test the gas, it is the litmus paper that must be damp or moist. Test for copper 2 ions, I add what? Add aqueous sodium hydroxide. We get a light blue precipitate insoluble in excess. So if he says he added drops of sodium hydroxide, we get light blue precipitate. Now excess sodium hydroxide precipitate remains. It is insoluble in excess. Test for iron. We have two types of iron. We have iron 2 and iron 3. If I want to distinguish between them, add aqueous sodium hydroxide. With iron 2, we get green precipitate insoluble in excess. With iron 3, we get red-brown precipitate insoluble in excess. Now, test for gases. We've talked about test for ammonia gas. We should insert damp red litmus. It turns to blue. Remember that ammonia is a basic gas. Carbon dioxide, test for carbon dioxide. We already said that if you add hydrochloric acid to a carbonate, it gives carbon dioxide gas. How do I know it is carbon dioxide gas? I bubble the gas through lime water. The lime water turns milky. Now please remember, what is lime water? Lime water is actually calcium hydroxide. Lime water is calcium hydroxide. That's a base. If we pass carbon dioxide through it, carbon dioxide is an oxide of a nonmetal, it's acidic, so it reacts with the base to give salt plus water. Now the salt formed here is calcium carbonate. Calcium carbonate does not dissolve in water, and that is why the solution turns milky. Test for chlorine gas, and I'm going to remind you again, we have test for chlorine gas and we have test for chloride. Chloride was the one where we added silver nitrate. But test for chlorine gas, we insert damp blue litmus paper. It bleaches. Bleaches means it becomes white. So we have two types of litmus paper, red and blue. But if you put the litmus paper in chlorine, and this is a gas, so it should be damp, and chlorine gas bleaches litmus paper. Test for hydrogen gas and oxygen gas. In both cases, we use a splint. A splint just simply means match. So, with hydrogen gas, we're going to use a lighted splint. So, test for hydrogen gas, insert a lighted splint, it pops, or it goes off with a pop. Insert for oxygen, insert a glowing splint. A glowing splint means I light the match and then blow a little bit, so it is just going off. If I put it into the oxygen gas, it relights. So remember, for hydrogen, we're using lighted splint. For oxygen, we're using glowing split. Then we have flame tests, and you should know, what do we mean by flame tests? Flame tests are tests for metal ions, and they are due to the fact that when I put a metal ion into the Bunsen burner flame, electrons gain energy, jump to a higher energy level, which we call an excited state, and then the electron returns back to its original energy level. Now, when it returns back to the original energy level, it emits light in the visible spectrum, giving a specific color. So, if I want to do flame test, how do we do flame test? First of all, we're using a platinum wire because platinum is inert. It does not react. So I'm going to clean the platinum wire by dipping it in concentrated HCl. Then dip the wire in the salt and then expose the wire to the hot flame, or sometimes we call it the non-luminous flame of the Bunsen burner, and observe the emitted light. Remember, we need to clean the platinum wire to remove any traces of previous ions to avoid contamination. The Bunsen burner flame should be hot, and in order to make it hot, we should open that air hole near the bottom. If the air hole is closed completely or slightly closed, not enough oxygen is reaching the fuel, so the flame is not hot. But in order to have a hot flame, the air holes at the bottom should be fully open. Now, when we do tests, the color indicates what we had. And remember again, these are tests for the ions, not the metal itself. So we're not testing for lithium or sodium or potassium. We're testing for lithium ion. That means a compound containing lithium or a compound containing sodium, and so on. So lithium gives red, sodium yellow, potassium lilac, calcium orange red, or we say brick red. Copper 2+ gives a blue green color. Please learn these colors. So if he says give a test to show that potassium nitrate in the test tube contains potassium ions, the test for potassium ions is flame test. So you just tell him do flame test. Do not explain how to do a flame test unless if the question tells you to do that. But if we're just saying a test for potassium, we tell him do the flame test. It should give lilac flame. Now give a test to show that a solid contains calcium ions. Again, we can do flame test. For calcium, we should get orange red or brick red color. Other tests, test for water. We have a chemical test for water. That means I have a liquid and I want to know if this is water or not. I add anhydrous copper sulfate. If it has water in it, the anhydrous copper sulfate should turn from white to blue. Remember that. Anhydrous copper sulfate means copper sulfate that doesn't have water in it. It is white. Now when we add water, it becomes hydrated, so it turns from white to blue. But if I want to show that my water is pure, or we're told to give a physical test for water, then heat the liquid to boiling. It should boil at 100 degrees Celsius. Test for alkenes. When we were talking about organic, we said test for alkenes, add bromine water. It turns from orange to colorless. And these colors you're required to know. So we talked about colors of group 7, fluorine, chlorine, bromine, iodine. These are yellow gas, green gas, reddish brown liquid, gray solid. And then you should know these colors of the copper compounds. You should remember that copper metal alone is reddish brown. Copper sulfate, blue. Copper hydroxide, blue. Copper chloride, blue. Copper carbonate is green. Copper oxide is black. And then we have magnesium oxide. We talked about magnesium being heated, burned in oxygen to give magnesium oxide. Magnesium oxide is a white ash or a white solid. Nitrogen dioxide gas is a reddish brown fume. Now we have two solid things in the syllabus. So if we are starting with an organic compound and we get a black solid, it's probably carbon. If we are starting with something that has copper in it and I get a black solid, then that is copper oxide. And when we are using a catalyst, this is a catalyst for decomposition of hydrogen peroxide, manganese dioxide is also a black solid. This is a typical question where he says bromine reacts with iron 2. Other elements in group 7 may also react with iron 2. Describe an experiment to find out if chlorine reacts with iron 2. So he's telling me bromine reacts with iron 2. Will chlorine react? How do I know? Well, he shows that if it reacts, the iron 2 will change to iron 3. So I can test. If it remains iron 2, then there was no reaction. If it changed into iron 3, then it reacts. So we say pass the chlorine through a solution of iron 2 something, iron 2 nitrate, for example. Do the experiment. He says relevant safety precautions. So when we're working with gases, we have to do the experiment in a fume cupboard to avoid exposure to harmful gas. Then we leave it to react, and then we test the end. We test it using what? To test for iron 2 or iron 3, we add aqueous sodium hydroxide. Now, if it reacted and it gave iron 3, then I should get a reddish brown precipitate. But if there was no reaction and the iron 2 remained the same, then we should get a green precipitate. Rates of reactions. You should remember that the rate of a reaction can be increased or decreased by what? Temperature. If we increase temperature, the rate increases, and you have to explain why. So increasing temperature increases the rate. Why? Because the particles gain more kinetic energy, move faster, collide faster, and more of the molecules have energy higher than activation energy. Remember that we said activation energy is the minimum amount of energy needed to start a reaction. So when the particles collide together, only the particles that have energy higher than activation energy would actually react. So when I increase the temperature, then more molecules have energy higher than activation energy, so more successful collisions. And remember that when we draw a graph to show the rate, so this is an experiment that's giving out a gas. Now when we did the experiment at 25 degrees Celsius, the rate was a little bit slow. But when we increased to 40 degrees Celsius, the graph increased rapidly. The slope is steeper. The new graph is above the one at lower temperature. If we're starting with the same amount of reactants, we end up with the same amount of product, and that is why the final volume of gas in both cases is the same. Pressure, you should remember. First of all, pressure applies only to gases. When we increase the pressure, that means I am pressing the molecules nearer to each other. This would increase the rate. Now, why would that increase the rate? Because when you increase the pressure, particles are closer to each other, so more collisions per minute. Remember, rate is determined by number of collisions per unit time. Surface area. If I use a big piece of magnesium, for example, or a big piece of copper carbonate or something, if I crush it into smaller pieces, then the rate is faster. And that is because as a big piece, only the particles on the surface are reacting. But when we crush it into smaller pieces or into powder, we say this has larger surface area because now all of these particles are exposed. So larger surface area, so more particles collide at the same time, or you could say more frequent collisions or more successful collisions. Concentration of reactants, if I increase the amount of reactants, that means I have more particles colliding at the same time. So using a more concentrated solution would increase the rate. Then, catalyst. To increase the rate, I could use a catalyst. A catalyst increases the rate of the reaction without being changed. That means if I start with a certain amount of catalyst, if it is a catalyst, I should end up with the same amount that I started with. It just speeds up the reaction just by being present in the reaction. Now, how does a catalyst increase the rate? You should know. A catalyst increases the rate of a reaction because a catalyst provides an alternative pathway for the reaction. That means it allows the reaction to happen in a different way. So it provides an alternative pathway for the reaction with lower activation energy. We said activation energy is the minimum amount of energy needed to start a reaction. Now, when we draw this kind of diagram, this is called an energy profile diagram. It shows that this, for example, is talking about an exothermic reaction in which the reactants give out heat, so products have lower energy than reactants. But in order to go from reactants to products, it has to have activation energy. Without a catalyst, the activation energy is very high. That means the reaction will be slow. But when we use a catalyst, the activation energy is less. Remember, activation energy is the difference in energy between reactants and the top. So, without a catalyst, the activation energy is higher than with a catalyst, and that's why with a catalyst, the rate is faster. If we look at the different profile diagrams for exothermic and endothermic, in both cases, using a catalyst will lower the activation energy. And in both cases, the activation energy is the difference in energy between reactants and the top, whether we're talking about exothermic or endothermic. And with a catalyst, that amount of energy is much less than without a catalyst. So this is a typical question where we say these solids catalyze decomposition of hydrogen peroxide. So he's giving me two solids and he's saying describe a method that the student could use to find out which solid is a more effective catalyst, which one is a better catalyst. So what should we do? You should know that when hydrogen peroxide decomposes, it forms oxygen gas. So how do we know which one is a better catalyst? We put equal amounts. So let's say at the beginning, we're going to weigh 5 grams of that first solid using a balance, put it into the flask connected to a gas syringe, then add a specific amount of hydrogen peroxide. So let's say 25 centimeter cube. This is usually using a dropping funnel so that as soon as I add it, I close the tap so that I don't lose any of the gas. Determine the volume of gas collected in a specific amount of time. So let's say in 2 minutes. Then you repeat with the same amount of the other solid. So if we started with 5 grams of the first solid, then repeat using 5 grams of the other solid. Same volume of hydrogen peroxide, same temperature. These are the things you're keeping the same, and the one that gives more gas in the same amount of time is the better catalyst. Please learn how to explain this. Studying rates of reaction, the volume of gas per minute may be measured using what? Well, that depends on the reaction. So if the reaction is giving out a gas, then I'm going to measure the volume of gas using a gas syringe. Remember that any reaction is fast at the beginning, because at the beginning we have a lot of reactants, so more particles are colliding. Then as the reaction proceeds, the rate slows down and becomes zero. Why? Because reactants are being used up, so less collisions. But please, when you're answering the question, go back to the beginning of the question, find out which reactant was excess and which one was limiting, and you have to say that the one that was not excess is the one that has been used up. So the one that is not excess or the one that was limiting is the one that has been used up. Again, if I do an experiment and I get graph A, what is graph 1, what is graph 2, and what is graph 3? You should realize that graph 1 is slower, graph 2 is faster, but in all of these three experiments, I was starting with the same amount of reactant, and that is why they all gave the same volume of gas in the end. Now, experiment 3 has more volume of gas, so obviously I started with more of the reactant. So, changing from experiment 1 to 2 to 3, remember, experiment 1 is slower, but experiment 2 is faster. So if we're doing something that makes the experiment slow, I draw graph 1. If we're doing something that makes the experiment faster, I draw graph 2. And in both cases, I'm starting with the same reactants. So what can I do to get graph 2? I can use higher temperature, higher concentration, higher pressure if we're talking about gases, crush the solid, use a better catalyst. All of this will give me graph 2 instead of A. Now, how do we get graph 3? We said to get more final volume of gas, that means we started with more reactants. If it is twice the amount of gas, that means I started with twice the amount of reactant. Another method of measuring the rate could be to measure the change in mass. Again, this reaction must be something that gives out a gas, because if the reaction does not give out a gas, there will be no change in mass. But if the reaction gives out a gas and the gas escapes, that's when we have the mass decreasing. So if we say, why is the mass decreasing? Because the gas is escaping. If we say, why do we have cotton wool at the mouth of the conical flask? We have cotton wool there to prevent loss of solution by splashing. Remember that any reaction that gives out a gas is always bubbling. So we could lose some of the solution by splashing. We put that cotton wool there to avoid loss of solution by splashing. At the same time, I cannot close it with a bung because I want to allow the gas to escape. Of course, if I repeat the experiment, which of these experiments is the faster one, 1 or 2? Of course, experiment 2 is faster because the mass decreased in less time. If the reaction is not giving out a gas, then it should be forming a precipitate. We should see something in order to be able to determine the rate. So this kind of reaction gives sulfur solid, and sulfur is a yellow precipitate. So to measure the rate of this reaction, I put an X on a paper, put the flask on top of the X, and look through the solution. So at the beginning, I'm going to add the two reactants, start a stopwatch and measure the time taken for what? As the precipitate is formed, it will be difficult to see the X that is below the precipitate. So we're measuring the time taken for the X to disappear. Again, if we do this several times at different temperatures, you should realize that at higher temperatures, the reaction is faster, so it takes less time. So the one at the higher temperature, which is on the right, this takes less time because it is faster, so the graph looks like this. This is a question in which he says a student uses this apparatus to investigate the rate of reaction between dilute sulfuric acid and excess of small pieces of zinc. So please note the zinc is excess. Now, this is the student's method. Use 50 centimeter cubed of dilute acid, add approximately 5 grams of small zinc pieces, quickly connect the gas syringe, record the reading on the gas syringe every 30 seconds, name a suitable piece of apparatus to measure the volume of sulfuric acid. Of course, to measure the sulfuric acid, we don't need it to be that exact. The question was saying, let's go back to the question, it's saying use 50 centimeter cube. It did not say 50.0. So if we don't want it exact, we don't need to use a burette or a pipette, we can just use a measuring cylinder. Now give a reason why the mass of zinc pieces does not need to be measured accurately. Well, we are using excess anyway, so we don't care exactly how much we added. Give a reason why the student quickly connects the gas syringe. Of course, we have to quickly connect the gas syringe to avoid any gas escaping from the flask. State how the student would know when the reaction stops. Remember, this is a reaction that's giving out bubbles of gas. So when no more bubbles of gas are formed, then we know that the reaction has stopped. Now, the important thing here is we have a graph. The graph shows the volume of gas collected in the syringe. They've already plotted the graph for you. Sometimes they give you the readings and tell you to plot it. And then they want to determine the rate at a certain time. Now, when you have a graph of volume versus time, and you are required to get the rate at a certain time, then we draw a tangent at that time. Do you know how to draw a tangent? That tangent is a straight line that is touching the graph at that point. So we're looking at 80 seconds. We draw a tangent at 80 seconds, and then to know the rate, I determine the slope of that tangent. Do you know how to get the slope of a tangent? The slope is y2 minus y1 over x2 minus x1 for that tangent. So the upper volume is 70 minus 20, and on the x-axis it's 150 minus 0. So the rate is the slope of the tangent. Units. What are the units? Centimeter cubed per second. We did the y-axis over the x-axis. So centimeter cubed per second. If we say explain the shape of the graph. Now remember, we said at the beginning what is happening from 0 to 60, the reaction is fast. Remember, at the beginning of any reaction, the rate is fastest. Why? Because there are more particles, more collisions per second or per minute. What about from 60 to 150? What is happening? The rate is slowing down. That is because he's saying from the graph. Remember, from the graph, how do I know? The slope is less steep, and that means that the rate slows down. Why? Because the particles are being used up. So less collisions per second. Now, What is happening from 150 to 240? The reaction has stopped. It has stopped because what has been used up? Remember the reaction we were saying, it's a reaction between dilute sulfuric acid and excess zinc. So which one has been used up? You have to mention. Don't say reactant has been used up. No. Which reactant? At the end of the graph, the curve levels off. That means the reaction has stopped, and that means the one that is not excess has been used up. So in this case, it is the sulfuric acid has been used up. So no more collisions. You could continue to say no more collisions. Okay, let's talk about reversible reactions. You should know that reversible reactions are reactions that go both forward and backward without going to completion. So, in most reactions, reactants give products and that's it. But if the reaction is reversible, then reactants give products, but then the products break up to form reactants, and then the reactants react again to form products, and so on. That is a reversible reaction, and when we have a reaction, we indicate that is reversible using this sign for the arrow. So an arrow going both forward and backward, that indicates that the reaction is reversible. So which reactions are reversible? We could have breakdown of ammonium chloride. Ammonium chloride is a white solid. If I heat it, it breaks up to form two gases, ammonia and hydrogen chloride. But then when the ammonia and hydrogen chloride react together, they again form ammonium chloride. Copper sulfate, we already used this as a test for water. We said the anhydrous copper sulfate that has no water is white. But when we start to add water, it becomes blue because it returns to the hydrated form. Now, what do I do to the hydrated to get it back to be anhydrous? If I heat hydrated, it becomes anhydrous. So, the white, I add water, it becomes blue. The blue, I heat it, it becomes white. So that is a reverse. So a reversible reaction will continue to go forward and backward until it reaches dynamic equilibrium. Remember, what are the conditions of dynamic equilibrium? The forward and reverse reactions occur at the same rate. That means rate of forward reaction equals rate of backward reaction, and concentration of reactants and products remain constant. So if I have a reaction, NO2 is a brown gas. If it forms N2O4, it becomes colorless. If it goes back to NO2, it becomes brown. It will continue going forward and backward until it reaches dynamic equilibrium, in which we are somewhere in between. The rate of the forward reaction equals the rate of the backward reaction, and the concentrations of reactants and products remain constant. Don't say remain equal. They're not equal. They are just constant. So the amount of reactants remain the same. The amount of products remain the same. So they remain constant. Okay, so how can we affect a reversible reaction? We can change pressure if we're talking about gases. So this reaction is called the Haber process. It is a reaction to make ammonia, in which nitrogen and hydrogen react to form ammonia, but then some of the ammonia breaks up to form nitrogen and then nitrogen and hydrogen react to form ammonia, and so on. So this is a reversible reaction. Of course, if we're trying to make ammonia, then we want this reaction to go forward. So we need to shift. We say shift the point of equilibrium to the right. I want it to go more forward to give more ammonia. I don't want the ammonia to break up. So what can I do? Well, this is a reaction involving gases. We can change pressure. You have to remember, increasing the pressure on any reversible reaction forces the reaction to go to the side that has less number of moles. This applies to any reversible reaction. Increasing pressure goes to the side with less moles. So in this reaction, if I increase the pressure, will it go forward or backward? Remember that going forward in this reaction forms 2 moles of ammonia. Going back will form a total of 4 moles, 1 nitrogen and 3 hydrogens. So in this reaction, increasing the pressure forces the reaction to go to the right. So we say it goes forward or it shifts the point of equilibrium to the right. That gives less number of moles. So if we say increasing the pressure in this reaction, what is the effect on point of equilibrium? We're going to say shifts the point of equilibrium to the right or forces the forward reaction. What is the effect on the yield of ammonia? Well, if it goes forward to give less number of moles, that means it's going forward to make more ammonia, so the yield of ammonia increases. Are we paying attention? Now, remember that we cannot increase pressure too much. So, for this reaction, I want more ammonia, I should increase the pressure. But remember that if the pressure is too high, the process is too expensive. So, we don't want a very high pressure. So, this Haber process is done at a pressure of 280 m. So, if we say, why not more? Why not 400? If increasing pressure gives me more ammonia, why not use 480 m? Because high pressure is more expensive since it requires specific equipment actually. Why aren't we using less pressure? Well, lower pressure will cause the point of equilibrium to go to the left or the reaction to go backward, and this gives less yield of ammonia. So, reversible reaction, this is a question between hydrogen chloride and oxygen, produces water vapor and chlorine. So, all of these are gases. Explain what effect, if any, the following changes has on the yield of chlorine at equilibrium. So, he's saying what happens if we increase pressure. Okay. Remember we said increasing pressure will cause the reaction to go to which side? To the side with less number of moles. So increasing pressure here will cause it to go forward or backward? Well, if it goes forward, it forms a total of 4 moles. If it goes backward, it forms a total of 5 moles. So actually, increasing the pressure in this reaction causes the point of equilibrium to shift to the side with less moles, so the reaction goes forward, and this gives a higher yield of chlorine. If we say another question, state the effect of increasing pressure on the equilibrium position of this reaction. Again, we said increasing pressure goes to the side with less moles. If I increase the pressure for this reaction, will it go forward or backward? Well, going forward gives 2 moles. And going backward also gives a total of 2 moles. So if the number of moles are the same on both sides, then increasing the pressure will have no effect. Are we paying attention? So we said increasing pressure goes to the side with less moles. If there is no side with less moles, then there is no effect. It will not go forward or backward. It will not favor any of the reactions. What about temperature? Okay, temperature, always remember, increasing temperature forces the reaction to go to the side that is endothermic. So if we're talking about pressure, we look for number of moles. But if we're talking about temperature, we look at delta H. Remember, Delta H negative means the forward reaction is exothermic. When I write a reaction like this and we say the delta H is negative, that means going forward is exothermic. And you should remember, in any reversible reaction, increasing the temperature goes endo. Increasing the temperature forces the reaction to go to the side that is endothermic. So if we say in this Haber process the forward is exo, that means the backward is the endothermic. So for this reaction, increasing the temperature for this reaction will cause the equilibrium to go to the left or backward. So it would give less ammonia. Do we understand that? So for this reaction, if I want more ammonia, I should actually use lower temperature. But the problem is, if I use lower temperature, the reaction rate is slow. Remember that increasing temperature increases rate. So for this reaction, if I increase the temperature, it goes back, gives less ammonia. But the reaction is faster. And that is why the Haber process, this reaction of nitrogen plus hydrogen to give ammonia, is actually done at 450 degrees Celsius. Now, why not less and why not more? We do it at 450. We don't want it less because at lower temperature, the rate is too slow. And we don't want it higher temperature because at higher temperature reaction goes back, less ammonia is formed. So what happens in this reaction is we do it at 450 and any reactants that are not used up are recycled over the catalyst. There's actually a catalyst in this reaction and it is reused. So if I have this reaction, HI given hydrogen plus iodine, and we are told that the delta H for this reaction is plus 9.6. What does that mean? That means that the forward is endo. So what happens if I increase the temperature for this reaction? Increasing the temperature for this reaction will cause it to go forward. So it will shift the point of equilibrium to the right, because it is an endothermic reaction. We said increasing temperature, it goes endo. What about this reaction? SO2 plus O2 to give SO3 is actually called the contact process, and we're told that the delta H is negative. Now, the temperature used is 700 K. Explain the effect of an increase in temperature on the equilibrium yield of sulfur trioxide. Again, we said increase in temperature, the reaction goes endo. Well, here the forward is exo, and that means the endo is the backward. So if I increase temperature, the reaction goes backward. Will that give more SO3 or less SO3? Remember, if it goes back, it will give less product. So the problem here is the forward reaction is exothermic. So increase in temperature shifts the point of equilibrium to the left or backward. So yield of sulfur trioxide would decrease. Another thing I can change is concentration. So remember, for any reversible reaction, if I add more reactants or I remove products, then I force the reaction to go forward. So adding more reactants or removing the ammonia as it is being formed, this will cause the reaction to go more forward and give more ammonia. If I add products or I remove reactants, then it will go back and the ammonia will break up to give nitrogen and hydrogen. So in this case, I want more ammonia, I can add more reactants, or actually what they do is as they form the ammonia, they remove it. so that the reaction is forced to go forward to make more ammonia. So in the Haber process, I'm trying to make more ammonia. So to force the reaction to go forward, the ammonia is actually cooled and liquefied as it has been formed in order to remove it from the mixture, and that forces the reaction to go more forward to make more ammonia, because remember, we want to remain at equilibrium in which we have a certain amount of reactants and a certain amount of product. So as we remove the ammonia as it has been formed, the reaction forms more ammonia and gives more yield. What about catalyst? If I add a catalyst to the reaction, remember, the catalyst will speed up both forward and backward reactions, so it has no effect on the point of equilibrium. So adding the catalyst would make the reaction faster, but it would not favor forward or backward, so it will not give more ammonia or less ammonia. It will just make the reaction faster. So, and one of these advantages of using a catalyst is that when you use the catalyst, the reaction is fast and you don't need to heat it to a very high temperature. Remember, we said this reaction, the forward is exo, so if we try to heat it to a very high temperature, the reaction goes backward. So instead of doing that, we use a catalyst so that we can use lower temperature in order to favor forward reaction without affecting the yield. So if we have this, explain what effect, if any, use of a catalyst has on the yield of chlorine. Remember, we said a catalyst speeds up both forward and backward reactions. So there is no effect on the point of equilibrium and no effect on the concentration of the product. It will not give me more chlorine or less chlorine. So remember, we said the Haber process is nitrogen plus hydrogen to give ammonia. What are the conditions used? We said we use 450 degrees Celsius, not too high, not too low, 280 M, not too high, not too low, and iron catalyst. For the contact process, that is the reaction of sulfur dioxide plus oxygen to give sulfur trioxide. Again, the forward reaction here again is exo, so we use 450 degrees Celsius, not too high, not too low. And we found that using 280 M pressure is enough to give a good yield of sulfur trioxide, so we don't need to increase a pressure too high. Remember, increasing the pressure too high is more expensive because it needs special equipment. So if 280 M is enough, that's fine. V2O5 is used as a catalyst. And that's the end of this part. We have just one more part in which we will be discussing the topics of organic chemistry. Thank you for listening.